Okay, I'm working on section 9.3, so find in your notes section 9.3. This section is all about relative rates of growth. So what function is growing faster than another function given two functions. So we're going to be comparing rates of growth. We may want to use L'Hopital's rule. That might be coming in handy when we do the comparison of the rates of growth. Also, it has a nice application to computer processing as well that we can talk about when I'm back. Quick review. I would like you to find the extreme values and where the function is increasing and where the function is decreasing. And our function is this quotient of e to the x plus x squared divided by e to the x. So take a moment and do that. You can pause this video. All right, welcome back. We are going to, I'm going to reveal what I have worked out so far, see if we ended up with the same derivative. My derivative turned out to be quotient rule, and a little simplifying, I noticed that I had an e to the x factor in common, so I brought it out as a GCF, and that allowed me to cancel with one of those bottoms when I squared the bottom. And so I get it into factored form here. Now, the next thing, let's find where the local extreme values occur. The local extreme values, if you remember from Calc 1, occur when the derivative is equal to 0 or when the derivative does not exist. When is our derivative equal to 0? Well, let's just take 0, set it equal to negative x minus 2 over e to the x. That would mean then that x is either equal to 0 or to 2. And what about the bottom? Would the bottom ever be equal to 0? E raised to a power will never ever equal 0, so we would not get a critical value from the derivative being d and e. We have two possibilities, and let's decide what kind of critical value they are. This is where we took things into a sign chart. So make yourself a sign chart. This is a first derivative sign chart. Put your two critical values on your sign chart and select some test points. You guys know the routine. We'd have -1, 1, 3, maybe as possibilities. And we take them back into the first derivative. So I'm bringing them back up into this, and if I put -1 in, I'd have a negative times negative is positive. Positive times negative will be negative. My bottom will be positive all the time, so once again it was a positive times a negative gives me negative. When I put in 1, I will get a positive because I'll have negative times negative. Putting 3 in, I'd have negative times a negative from here, and this will turn out to be positive. Negative times positive will be negative. We now can determine that this is a decreasing function from negative infinity to 0, increasing function between 0 and 2, and decreasing function after 2, so 2 to infinity. I then can spell out what the extreme values are. We have a relative max, min, oops, and then a relative max because it's going up and falling after it. And that kind of completes it. We kind of answered B and C as we were drawing our sign graph talking about it. If you had to justify why something was increasing, your justification would be because your first derivative was positive. Remember, for the AP test, you have to write out those justifications. They will not read your sign chart, so you have to interpret. All right, let's get into the crux of the matter here. Faster, slower, same rate growth, and we're looking at our functions as x goes to infinity. So as we move far to the right of our functions, what is the comparison between f of x and g of x? So just reading this through here, it says let f of x and g of x be positive for x sufficiently large, F grows faster than G, or we could say G grows slower than F, just a different comparison. As x goes to infinity, if, now here's how we're going to do the comparison. We're going to let the limit as x goes to infinity be determined by comparing f of x over g of x. Or equivalently, we could put g of x over f of x. It doesn't matter which one you put on top. Either way will be fine. But the interpretation then, if one is growing faster than the other and f is on top, then my limit will be going to infinity because f is growing faster, getting larger more quickly. If I have my functions reversed and f is growing faster, then that should take this quotient to 0 because g divided by something that's much larger will end up being 0. I think you're going to be able to interpret your results quite easily. You're going to know if it goes to infinity, that's because the top headed to infinity. If it goes to 0, that's because the bottom was growing so much more quickly. All right, and then step number 2, other options, we could have f of x growing faster or slower than another function. What's the other alternative? They could grow at the same rate, couldn't they? How would I know if they're growing at the same rate? Well, it says look at your limit, let x go to infinity, do the comparison, and you end up with L. What? What's L? L is just some limit. So we actually get a numerical value. If you end up with a numerical value, they are growing at the same rate. All right? So that's really the whole design of it. So compare e to the x and x to the third as x goes to infinity. We want to show that the functions, how about just function, e to the x grows faster than x cubed as x goes to infinity. So we can compare either way. I can either let e to the x be on top or e to the x be on bottom. I've got it set up both ways through part A and part B, and it's going to be quick to run through. You know, if we evaluated throwing infinity in, we would definitely see infinity over infinity, which tells us that we may use L'Hopital's to determine the limit. So the limit as x goes to infinity, I would take the derivative of the top. Well, the derivative of e to the x is e to the x. Bottom, we get 3x squared. And gosh darn it, we're still infinity over infinity. Do it again. So if I do another L'Hopital, we will have e to the x over 6x, which still is infinity over infinity. You know where this is going. Keep doing enough L'Hopitals. E to the x over 6. Awesome. We finally got the bottom down to a constant. And if I allow my analysis at infinity, I get e to the infinity, which is large, divided by 6, which isn't so large. This would go to 0. Now what I have to do is interpret what this means if my limit goes to 0. If the limit, oh, how did I do that? Back up. Infinity divided by 6 would still go to infinity. So interpreting how that happens, it means if my answer is infinity, then it was through the numerator growing so quickly, more quickly than what the bottom was. So I now know that e to the x is growing faster than than x cubed. Sorry about messing that one up. All right, on to B. What if we twisted them around? Well, we know we have infinity over infinity. Means we'll use L'Hopital, so we'll do a little L'Hopital action here. The limit as x goes to infinity, take a derivative, e to the x, take another derivative, 6x over e to the x, take another derivative because we're still infinity over infinity, and we get 6 divided by e to the x. Now I get 6 divided by e raised to infinity. That is 6 divided by large. 6 divided by large will go to 0. Interpretation. What does that mean? Well, if the limit of this goes to 0, it is because my bottom grew so much more quickly than what the top did. So once again, same statement, e to the x is growing faster than x cubed. I suppose you could turn around and say 3x squared. When is that 3x squared? X cubed is growing slower than e to the x if you wanted. This one says, show that ln x grows slower than x. You can select whichever way you want to design. We want to look at the far right reaches, so we're going to let x go to infinity. I'm going to throw x on top over natural log x. And if I do that, I get infinity, put in natural log of infinity. That'll be infinity. All right, go into L'Hopital's. Let's see if we can evaluate this limit. Derivative of the top would be 1. Derivative of the bottom is 1 over x, which makes this look like the limit as x goes to infinity of x. That would take us to infinity, wouldn't it? And if I'm headed to infinity, then f of x is growing faster. The top function is growing faster if I get an answer of infinity. Well, my top function, go back to the beginning, right? We had set up that x was our top function. So we now know order of business. X grows more quickly, grows faster than natural log x. Or conversely, natural log x grows slower than x of x. Let's do a comparison of x with x plus sine of x. And we can set it up either way. I think I'm going to make g of x my top function. So the limit as x goes to infinity, we would have x plus sine of x divided by x. I would get infinity over infinity, wouldn't I? And I could use L'Hopital. Why not? Let's use L'Hopital. So we would get the limit as x goes to infinity of 1 plus cosine of x divided by 1. The top, oh, this gets tricky, doesn't it? The reason I said it gets tricky is, what is the cosine of infinity? That's a stumper, isn't it? I know one thing, it can only waver between -1 and 1 because those are the range values for cosine. And is that helpful? A little bit, but I think I'm still going to have issues. So maybe that isn't the best method, and I know you're cringing right now. But this is what mathematicians do. You try things. Let's scrap that plan. I've got another plan. Follow me on this line of thought. Let's take the limit as x goes to infinity, and we still are going to work with this x plus sine of x over x. But, heart this baby out. Single solo denominator allows us to go the limit as x goes to infinity of x over x plus sine of x over x. And you should be loving this right now. Simplify. We get the limit as x goes to infinity of 1 plus sine of x over x, which means that we really can analyze each of these separately, right? I can say that I've got the limit of 1 and the limit as x goes to infinity of sine of x over x. First one's easy. How about I do the first one, you do the second one? All right, first one, I'm going to go right underneath it. This we know is 1. the limit as x goes to infinity of 1 is 1. In this one, we can use that same logic about sine, that it ranges between -1 and 1, right? The range of that function is -1 to 1. So if I take either of these numbers and divide it by something large, it's going to go to 0, and it's either going to go to 0 from above or below, but eventually it's just going to sit there and waver, but be so close to our axis that we will get +0 there. So it appears to me that we get 1 as our answer. The limit of x, or as x goes to infinity, of x plus sine x over x equals 1. How do I interpret my results? Well, this is that L value, right? When we read the script in the beginning, a page back, where was the bookwork? F and G grow at the same rate as x goes to infinity if we get a number. So it turns out that these functions grow at the same rate. Page up here. So conclusions. So x and x plus sine x grow at the same rate. Yeah, never give up. Try a different route. If the first road led you to some difficulties, try a different path. Sometimes it will get you there. All right, number 10. Show that x squared grows at the same rate as the given function. And so I have f of x is x squared and g of x. Which one do we want to put on top? I'm going to vote to put my square root on top. So I'm going to have square root of x to the 4th plus 5x divided by x squared. Do you recall, you guys, when we did that analysis way back in Calc AB, that, okay, the big players are going to be the things with the largest powers. So on top, x to the 4th is way overpowering the 5x, so I can almost ignore 5x. If I take the square root of x to the 4th, I get x squared, don't I? And I have x squared over x squared. My gut feel is that this thing is going to turn out to be 1. And I bet you have the same thoughts. Let's see if we can maybe process it just a little bit more carefully, more algebraically, than just, thinking things through. Whoops, one too far. All right. How are we going to deal with this? Well, we could get the infinity over infinity thing, try L'Hopital's, but look at this as a technique. Here's another approach that you could take. I want to make one big square root. Can I do that? Well, yes, as long as I make it equivalent to what it originally started out as. So if I'm going to add a square root over this x squared, it's still got to come out as x squared. What must I do? Well, then I have to make this a squared squared. So x squared squared, square rooted, would look like x to the 4th square rooted, and indeed that turns out to be x squared. So no harm done. Let's make this an x to the 4th then. Transfer x squared to make it x to the 4th with a big square root. Now, how is that helpful? Well, once again, loving it because we can split things up, can't we? That technique often is super helpful. So splitting things up, x to the 4th over x to the 4th plus 5x over x to the 4th. Well, obviously the first one is going to turn out to be 1, the limit as x goes to infinity. And don't tell me we can bring that out of the square root. We can't with the plus sign. And I'd have 5 over x cubed, right? Analyze, substitute. We get square root of 1 plus 5 divided by something large. And I'm not going to mess this up. I'm going to get 1 plus 0. Haha. And that gives a square root of 1, which is 1. Hey, it's what we thought all along, but we have evidence behind it. These things do grow at the same rate. This turned out to be a numerical limit, and that's just what it takes to say that x squared grows at the same rate as square root x to the fourth plus 5x did. Cool. One to go. So, transitivity of growing rates. What the heck is transitivity of growing rates? Well, let's read the, I'm sorry, I'm reading my notes. Transitivity of growing rates. If f grows at the same rate as g, as x goes to infinity, and g grows at the same rate as h, as x goes to infinity, then f grows at the same rate as h. Hey, it's kind of like that transitive rule. If A was equal to B and B was equal to C, then I can connect and say that, therefore, A is equal to C. Transitivity rule of equality, I think, was how it's worded. It's that same notion. If I can kind of compare to something that they have in common, then I can make a comparison between the outer two functions. So our example, growing at the same rate. Show that f of x, which is the square root, and g of x, which is 2 square root x minus 1 quantity squared, grows at the same rate as x goes to infinity. Rather than doing a direct comparison like we have been doing, like we've been putting f of x over g of x, let's introduce another function. So we're going to bring in an additional function. So let us introduce another function. Let's call her h of x. H of x, and what function do we want to make it? Something easy. Let's call it x. So now I'm going to use this transitive idea to do that. Oh, dang it, I didn't see it was right there. Let's see. The limit as x goes to infinity of square root x squared plus 4 divided by my x is equal to infinity over infinity. But we just saw the trick on the last one where we made a big square root, let it house them both, pump up the bottom so that we can bring it under. Let's bring it under then as x squared. Separation gives us x squared over x squared, or 1. Make that a 1. Save a little space. Plus 4 over x squared. Well, we know this limit is going to 0. So the square root of 1 is 1. That means that those two are growing at the same rate, right? Conclusion. I'm gonna put it in terms of, I'm trying to decide, guys. Square root of, I was gonna say f of x and h of x, but I changed my mind. Square root of x squared plus 4 and x grow at the same rate. Just kind of for our own purpose there. What's with the double dot? All right, now we need to pick up and do the other function, the g of x function. And we've got to compare it to h, so that we're comparing against the same thing. And that function was 2 square root x minus 1 quantity squared. And we're comparing it to what we compared up here, our x, the h of x1. What would be a great technique on that? Good question, huh? Well, you know, the big square root worked so well before. Let's try a big squaring. I would love to make this a nice little fraction inside and have the squaring going on outside. So in order to do that mathematically, I don't want to put x there because now it became x squared. But it is going to get squared, so let's slip in a square root. Did you see that? I did it so fast. Well, let me repeat it. Throw in a square root. Because now square root squared becomes back to just simple x. Now, separation. You gotta love these. That wasn't a very good heart. The limit as x goes to infinity gives me 2 square root x over square root x, loving that one, minus 1 over square root x, all to the second power. Okay, evaluate that. The limit as x goes to infinity. Let's see, we can cancel, can't we? So we get a 2 minus 1 over infinity quantity squared. That makes 0. This is going to 0. So basically 2 squared makes 4. It is a number limit, isn't it? Therefore, they're growing at the same rate. So I know that 2 square root x minus 1 quantity squared and x grow at the same rate. So by comparison, or by the transitive property, if f of x and h of x are growing at the same rate, f of x and h of x grow same rate. And we also know that h of x and g of x grow at the same rate. The conclusion would obviously be that f of x, so therefore f of x and g of x grow at the same rate. Ta-da! I like that one. Hey, one other thing that you might find interesting. I could write this the limit as x goes to infinity. We compared f of x to h of x multiplied by h of x over g of x. Could have done that, couldn't I? But through the cancellation, I end up with the limit that does compare f of x to g of x, right? I mean, you can kind of see the logic behind that. So that transitive property really does turn out nicely. And through properties of limits, we could have written this as individual limits, f of x over h of x. It's sum times the limit. It's sum, it's result. And we could go h of x over g of x. Multiply them two. Anyway, they grow at the same rate. And that is plenty. I know you're probably sick of me. We'll talk about that when we get back in. So here is the homework. You can work on page 461, and you've got the better part of an hour to do that. Hey, have a good weekend. See you on Monday.